we've seen that chemical reactions can absorb or release energy. We can say how much energy they're absorbing or releasing by using reaction enthalpies. We can measure reaction enthalpies using calorimetry. But what we haven't talked about yet is where does that energy come from? How come some reactions release energy and other, like fires, and some other reactions absorb energy, like the reactions that happen in a cold pack? Let's think about a problem that I used to work on that involved spacecraft re-entering the atmosphere. So here is a space plane. It comes down through the atmosphere belly first, and it makes a shock wave in front of it. Now, part of the idea of slowing the craft down as it re-enters the atmosphere is that some of its kinetic energy is going to go into driving chemical changes that happen in the shock wave. In particular, what happens in the shock wave is that N2 molecules that are in air turn into separated nitrogen atoms. O2 molecules turn into separated oxygen atoms. Now, these processes involve breaking bonds. And these absorb so some of the kinetic energy of the spacecraft disappears because it's driving these reactions. It's breaking these bonds which require energy and absorbs some of the kinetic energy. Unfortunately, though, some of these free nitrogen and oxygen atoms will go and hit the heat shield on the bottom of the spacecraft, and they will join up again. So on the heat shield here, you have the reverse reactions occurring. Whenever a couple of oxygen atoms meet up on the heat shield, they can form an O2 molecule again. Now you've made a bond. That energy will appear as heat. And the surface of this was lined with material something like spun glass, and it was hot enough for it to melt. In fact, it's hot enough to melt a lot of metals, in particular aluminum, which the rest of the spacecraft is made out of. So if the ship does not come down belly first like this, if it came down a little bit wrong, upside down or sideways, there'd be enough heat from this process that's generated to actually destroy the spacecraft, and that did happen once. You can also get this reaction happening, and it's also going to release energy. Now, we can go and look up how much energy is absorbed or released by this reaction. Let's see. If you take a look at question 7 on your worksheet, it says that the bond energy, the bond enthalpy for N2 is 941.4, and that means that I can write that this reaction releases 941.4 kilojoules. Now notice what I've done here. I've taken the chemical part and I've added a thermal part. So this is called a thermochemical equation. And when I make a bond, it's going to release energy, so I know there has to be a minus sign on there. And this amount here is what I've got for forming a triple bond. If I look at this reaction a little bit more closely, I have two nitrogen atoms forming an N2 molecule, which if I draw the Lewis structure for it, which we've done many times, so I'm going to do it pretty quick, looks like this. So I am forming a bond, and every bond that I form, the bond energy, and we're using enthalpies here, kilojoules. So if I'm forming one bond, delta H is forming a bond that's worth this much. You can think of it as each different kind of bond you have can release or absorb a certain amount of energy. And if you look at your table in question 7 on this worksheet, you will see some of the values that you can have. If you take a look at the worksheet, you'll notice that you've got like carbon-carbon bonds there, carbon double bond carbon, carbon triple bond carbon. And if you look at the bond enthalpies for those, the carbon-carbon bond has 347 kilojoules. The double bond has 620. And the triple bond has got 812. What does that tell us? This is how much energy it takes to break that bond. If you form that bond, this is how much will be released. If you break that bond, this is how much energy it will take. And a single bond is easier to break than a double bond. A double bond is stronger. And I can see that from the bond enthalpy. The higher the bond enthalpy is, the stronger the bond. Now I can relate the reaction enthalpy to the delta H, the reaction enthalpy, the delta H, to the bond enthalpies. I can look at what bonds are being broken and what bonds are being formed to figure it out. For example, with this one, I've got O plus O. There's no bonds there, but it's forming O2. If I do the Lewis structure for that, I can see that there's a double bond in there. So there's no bonds broken. There's one bond formed. And if I look at the O double bond O number, it's 498.7. Since the bond is formed, I'm going to put a minus sign in front of that, because any time that I make a bond, that releases energy, and released energy is negative. All right? So if I add the enthalpy I get for the bonds broken to the enthalpy I get for the bonds formed, I'm going to get minus 498.7 kilojoules overall. That sum of those two things is going to be what delta H is for the reaction. Now, if I look up here at the reverse reactions, I can very quickly see that here, this is the same reaction that I have right here, but it's flipped over. The N2 is having a bond be broken here. So what's delta H for this reaction? It's going to be the opposite sign of what I have here. If I flip this part of the equation, I'm going to flip this part of the equation too. And it makes sense that that be a positive number because I'm breaking bonds here. Breaking bonds costs energy. Making bonds gives it back to you. What do you think, if you're following this, the delta H for this is going to be? For this reaction? Well, we figured out that delta H for this reaction here is minus 498.7. And this is that same reaction flipped over. So here it's going to be plus 498.7. When you break a bond, you put a plus sign in front of the bond enthalpy. When you make a bond, you put a minus sign in front of it. And you add all of those bonds being broken and being formed together, and that will give you delta H. So we explained where delta H comes from. In the last video, we'll do a more complicated example of this.